Thanks for coming to my talk. Grateful to be here with you guys. My talks definitely kind of focus more on the beginner to intermediate level of things. Some parts will be maybe diving into a little bit of the advanced side. But overall, I'm hoping to kind of get you guys excited to building with Nix OS. Do some deep dives into TinyGrad, some machine learning, and talking about the dev kit. And overall, hope it's a fun talk for you guys. And we'll be using a lot of tools other people built. Some of the stuff I did we'll go into at the end. I ported some backend stuff for drivers on the dev kit for TinyGrad specifically because they have drivers that work for desktop GPUs. So we'll get into that specifically, but a lot of the stuff we're talking about, as the title says, are tools other people built. And oh yeah, and fun can be a little bit of different things for everyone. For me, the fun parts I thought would be fun to show you guys. We'll go over some of the Nix stuff. We'll do some simple models. There's an academic paper I want to show you guys with a drone racing where they used a single IMU sensor to tell where the drone was. We'll talk a little bit about the machine learning with that. And then the hacking side of getting that driver to work. So hopefully you guys enjoy it. And then we'll get started with the Jetpack, the Nix OS side, and then we'll dive into the TinyGrad. So what is the dev kit, right? I skipped. The dev kit used a lot in robotics. And little story time. Last year was my first PlanetNix. And at the time, I had worked doing some LXC containers on these dev kits. And when I was at PlanetNix, I actually ran into an engineer here who built, and he's here today, he actually built the whole repo that you can get NixOS running on these devices. And I remember thinking, man, I wish I had that, right? Because when you're working with Nix, it's declarative, pure functions, all the things that we love about it, right? And anyways, here I am today giving a talk about it. So be kind of fun. And hopefully one of you guys will be giving a talk maybe next year. So the Jetson Orin, they have different classes of modules. I have the dev kit here up front. They have different sizes depending on what it's being used for. Some common examples, these are some companies that are using the Orin modules, Zipline, delivery drones, Anduril, they use it in some of their products. You see it in a lot of robotics, a lot of machine learning, edge compute. That's what these devices are really, really good at. That's what NVIDIA sells them for. Like I said, there's different classes. Only thing I wanted to draw your attention to here is this dev kit is on the Ampere architecture. So NVIDIA has different architectures for GPUs. Ampere will be important later because TinyGrad already did work to run their stuff on Ampere as well as other architectures. But a lot of the heavy lifting was already done for TinyGrad to get things running on Ampere. I should mention right now, we're going to be skipping CUDA runtime, and we're essentially reverse engineering the drivers to talk directly to the GPU, so you get a little bit of a overhead save. Although we'll get into it. Ampere architecture. There's a lot of other details. This is one of the parts where we maybe dive a little deep for beginner to intermediate level. I checked this morning. NVIDIA's worth $4.42 trillion for good reason. They do a lot of engineering. There's a lot of other details here. We're not going to talk about all of it. We're just going to highlight a few of them, a few key terms. Here is the Ampere on the dev kit. This is the kind of structure layout. Lots of acronyms, right, in computer science. Some of the main ones I wanted to mention are the SMs, the stream multiprocessors. And within those, they have 128 CUDA cores, 4 tensor cores, and warps are the unit of single instruction, multi-threads, how those execute on the device. Fun little historical fact, they call them warps. It's actually named, this is from Wikipedia. Warps are named this way because it's 32 threads, and they're all working together at the same time. And it's named after the weaving pattern with threads where you can make, there's warps and wefts, and that's how you make like different cloths and stuff. So random little fact. And then also just another kind of a high level, CUDA cores, this is somewhat simplified, but in general, they do one scalar operation per cycle. In the tensor cores, they can do it's a matrix, it should be multiply and accumulate. They can do a whole matrix op per cycle. So that's one of the big differences with those. And as I mentioned, when we're talking about GPUs, you'll often hear these 3 categories of bottlenecks. There's compute bound, memory bound, and overhead bound. Compute bound is generally determined by how many CUDA cores and tensor cores that you have, right? That's determined by how fast you can run. Memory bound has to do more with, your bandwidth speed, how fast are you moving things, or how fast are you moving memory around. And then overhead bound is actually not mentioned as much. And to be fair, depending on your model, you're not ever really going to worry about overhead bound. But for some smaller models, it can be a factor. And when you're kind of looking at your full software stack, if you're able to reduce even some system calls, or, if there's definitely some small gains to be made there. Oh, and then GPU glossary, good website, check it out. More there to that. But we'll dive into the overhead bound. Okay, so tools other built. Wanted to give a shout out, not to maybe embarrass him, but Daniel's actually here. This is his repo, and it's Andrew's repo. Yeah, give him a clap. So, and in a funny way too, not only in the title, but even when I submitted this talk proposal, I was like very explicit. I was like, hey, I use this tool, but this is like not my repo. And like TinyGrad's, I build on it, like I've forked it, and I've made some changes I hope to get upstream. But I was very explicit in the talk. I was like, don't think I built this, but I do use it. It's a lot of fun. And if anything, they did all the hard work for us. So huge thank you to them. They deserve all the credit, all their flowers and more. And if you want, the QR code takes you to there. Give them a star. So yeah, they did the hard work. They packaged everything we need. Firmware, the NVIDIA calls it the Jetpack. It's their SDK. Pretty much everything is so nice, so packaged. And the only one I wanted to highlight, he even actually happens to have it in his README. It's one of those drivers we were talking about. Because the dev kit is a system on a chip, it's going to have some slight differences between a desktop GPU. And so we'll get into that again later. But even this driver, he has it all there. It's great. Even this slide, just wanted it to look so simple. It really was. It was so pain-free getting this up and running. If you're used to working in NixOS, maybe 10 minutes of reading on the README, follow the steps. You just need a USB, your configuration.nix if you use flakes.nix. So pain-free, I literally, honestly, I kind of forgot most of the steps because I did it once and we're up and running, so we're good. But to highlight a few things he did, or that they did in the repo, in their make overlay.nix, this takes in versions that you want for Jetpack, Linux for Tegra, CUDA, and then outputs a make scoped package set. So it does a lot of the hard work, heavy lifting there. And then overlay.nix calls that function, that nix function, for each Jetpack version. This is a screenshot from Jetpack version 6, which is for this dev kit. So again, honestly, even skipping past that, all that hard work means it's easy for us. We get a declarative build, and all we have to do is include the overlay for the Jetpack version, and we get the overlays for the CUDA packages, and everything is just so nice, so easy. Yeah, everything we love about NixOS and more. Okay, from here on out, we're going to be talking about TinyGrad. Just know, under the hood, I'm using Nix Flakes, but we're going to be mostly focused on the TinyGrad side of things here. So TinyGrad, check them out on X. One of their mission statements is to commoditize the petaflop, and they're pretty cool. Check them out. Highly recommend it. So TinyGrad, deep learning, machine learning framework. They have a PyTorch-like front end, so if you've ever written code in PyTorch in Python, you'll feel very at home working in this. And they're first principled, bitter lesson pilled. Their repo is under like 20,000 lines of code, so it's very approachable, especially for everyone sometimes approaches things from a different point with like what they know in software or maybe their strengths and weaknesses. It's such an approachable repo that you can dive into it, really get into the fundamentals of how things are running, and we'll go over that in a later slide. But just know that they have very few dependencies, and when you compare them to some other frameworks, it's very first principled. This will probably at the end, maybe if there's time, I'll demo. But getting into some of the fun parts, right? TinyGrad has an example of the YOLO real-time object detection. I can run that later, but cameras, you get your real-time object detection. This is a common one. Fun stuff. But again, even working with, I brought the camera and an IMU sensor here today. NixOS, just compared to Ubuntu, really love it. We get everything we love, declarative. We avoid, you get also your system's atomic, so you're able to switch things out so easily, so cleanly. It's just, again, everything we love. And then just recap, the IMU, inertial mass unit sensor, it can measure with the accelerometer and gyroscopes. It's measuring the acceleration in 3 directions, X, Y, Z. and it's going to give you your angular velocity in directions as well. And this is, wanted to mention this specifically because one of the other fun things I wanted to go over was this drone racing paper. So this paper, they actually took a drone and they were able to get, if you look at the dotted black line and the blue line, the dotted black line is the ground truth where they have cameras, so they measured where the drone was. The blue line is the model's predicted like position of the drone, and they did that with only the IMU sensor. No other cameras on the drone, nothing else. Pretty high accuracy, only with the IMU sensor, and your software is a neural network, and you're technically in an extended Kalman filter, which just helps with noisy data as well as noisy sensors and kind of massaging that in. But we'll talk more about the neural network, and I just wanted to play their video real quick here, if it plays. Hopefully, even if there's no audio. Basically, you just see it's flying through. Again, it's still being flown. It's not being flown by the model, but they're able to predict where the drone is only with that one sensor, just like one of those sensors I have over here. So pretty cool stuff. And then just wanted to give them a shout out. It's a paper from University of Zurich. This paper was from a few years ago, and these were some of the researchers that were on the paper. I'm not good at pronouncing names, but wanted to put them up here, give them their credit. And they open source their code, so a lot of the stuff I was able to just go to their GitHub and pull their code and run with it. So again, definitely some details. We're gonna kind of simplify things. We're gonna look at just first principle things here, because in systems engineering, there's lots of knobs you can turn. There's lots of pros and cons. But in general, really, actually, the part you want to focus on, the neural network, it's looking at a buffer of data, and it's running a TCN, a temporal convolutional network, or neural network. And basically, it's trained over time. You can train the model to, it basically gets trained on the actual data and the error, and over time, you help it learn how far off it was depending on what buffer it was seeing. And then it's able to send that update to the extended Kalman filter. And those two combined, they were able to get, they were within 56 centimeters, but that's when they're traveling at 19.4 meters per second. So 43 miles an hour. So again, pretty remarkable. You're only using one sensor, just the IMU. Pretty remarkable stuff. And we'll just take that neural network and kind of run with it here in TinyGrad here in a little bit. Just that piece. Because again, if you take that neural network, this is somewhat in principle. You would hope if you can speed up how quickly you run a neural network, you might be able to get better performance as far as like how quickly you're able to get those updates and so forth. Again, somewhat of a simplification, but something at least to consider, something the paper can to get us to consider here. Okay, and then yeah, so we're gonna do kind of a walkthrough here now of some of the internals of TinyGrad, how your code goes from Python all the way to the device, and then this will help us see what the the TinyGrad backend helps us do, and it goes back to that overhead where we're avoiding some of the CUDA runtime, and we're able to essentially set up through ioctls everything we need to avoid any system calls, and we can talk essentially straight to the GPU. Okay, so you write your code in Python, right? You got your tensor operations. That gets turned into this graph, our DAG, directed acyclic graph. It's an abstract syntax tree. This has the IR that TinyGrad uses for representing different, like multiply, additions, reduce, different things. It's 20 to 30 ops, somewhere in there. You take that graph, you're going to try to fuse things together. Because at the end of the day, the kernel is what you're running on the GPU. So you're trying to take that, fuse them together. Your goal is to get things to run faster on the GPU. From there, along with those fusions you're doing, they're going to perform this is TinyGrad specific, they're going to perform a beam search, where you're actually just taking different kernel variants and you're testing them. And you're just performing a search. And you're just saying, who ran fast? And then you go to the next one. And then if one ran faster, you kind of keep going down that path. And you can adjust that as needed to try to find faster things to run. From there, that gets turned into PTX assembly. So another IR, PTX assembly is NVIDIA's parallel thread execution instruction architecture. So that is now in a form that we're going to be able to compile to a cubin elf, and then that's going to be able to run on the GPU itself. Then, after the compiler, this chunk right here, this is TinyGrad specific. And if you'll notice, we're not passing off to the CUDA runtime to get to the GPU. We're actually going to do it essentially all ourselves. And there's some details there, but I kind of want to highlight, I put the diagram on the left because it helps me keep track of things, because there are lots of acronyms. But at the end of the day, most of this stuff, they're often just buffers with metadata and pointers. And so we'll get into the doorbell here in a moment, but just know if you do your right ioctl calls, you get a doorbell, and if you put things in the right spots, you can ring the doorbell. No system call because you're using a user space call. And so you ring the doorbell, and it's going to run what you put in this lower left corner, the GP FIFO. It's the ring buffer for the GPU. So you're gonna that ring buffer has a pointer that points to the push buffer that you made, and that push buffer has wait, send, and signal. That send has a pointer that's going to point you to the QMDs. QMDs have other metadata, and those are going to have a pointer to the cubin elf that we compiled earlier. So again, kind of a long slide. Just wanted to show it as far as first principle. This is kind of the high level, how things are going through your system from Python down to the bottom. And by having that doorbell set up for us, we're able to reduce the overhead when we're running certain models that can take advantage or can see performance gains in that area. And then, yeah, so the NV backend. And TinyGrad is really good at writing accelerators for different devices. This one specifically I highlighted, so they already did the hard work for us. Everything with the push buffers, all of that code is essentially all there. All that needed to be done was figure out how to get that to work. Well, actually, really all that needed to be done was figure out the ioctl calls, so you can set everything up so that you're ready to take advantage of writing to the push buffers, writing to the ring buffer, and using all of that stuff. Okay, so how did I work on it? So this is one of the parts that I was mentioning earlier. This was fun for me. A little bit about me and my background. I did my master's degree at ASU. Some of the professors at ASU, they're part of a group called Order of the Overflow, and that group hosted DEF CON in Vegas, and they were in charge of essentially planning the competitions for the hackers. Those professors were fantastic, phenomenal, and they actually make a website now that they use to teach their classes. It's pwn.college. Highly recommend it. It's all free. Fun fact too, they do use Nix for their infrastructure. And I did at least one of the fun show and tells. They now use it for a lot of their classes, but when I was there, they were still building it. But if you go and do the challenges, they will actually give you a belt, and it has it embroidered on it, Pwn College. I've done the first two for fun. I'll have to work on the other two sometime. Highly, highly recommend it. And so some of my courses that I took from them, I'm very comfortable with working with system traces, right? Really comfortable with a lot of the different hacking sites, GDB, Binary Ninja, Ghidra, IdaPro, all that stuff. To be fair, though, we actually didn't necessarily have to do very much of that because this was kind of mostly a pattern matching problem. NVIDIA actually open sources that open source driver. They have the header files open sourced. And then TinyGrad also did essentially all the hard work, and we just needed to kind of bring it all together. And I put in a GitHub Copilot because, like everyone, right, and you'll probably hear it at all the talks, this was a project where I kind of knew roughly the path I had to take, essentially doing system calls, getting the system traces, looking at the ioctl calls, just making sure you follow the right order, making sure you match everything up properly. Not necessarily super hard, but can be time consuming. And this was one of those fun ones where, anyone that's gotten had some fun with the AI, it really helps speed things up. A lot of fun to work with, and really, really enjoyed it myself personally. So putting all that work together, there's 39 ioctl calls, and these ioctl calls you do once at the very beginning. some of them have to be done in a certain order because this is a system on a chip. It has shared memory, and so both the CPU and GPU are using the same RAM. And along with that too, there's a couple steps that have to be done in order. If you remember with like CPUs, right, you have your page tables and you have virtual memory, and then the GPU has its own kind of version of that. So there's certain calls you have to set up, but as long as you do them in order, one of the big ones, the setup bind one, if you're able to get to that, then you're going to be able to submit in user mode. And that means we don't get the overhead of Linux system calls, so we don't have to go down to the kernel. And everything's essentially ready to roll. You just have to ring, often called the doorbell, but you just have to ring the doorbell through the MMIO register. You ring the doorbell, and the GPU, since you set up, I'll go back, since you have essentially your snake of all your pointers and different metadata in the right spots, you ring the doorbell, and the GPU can essentially go do everything it needs to do. So this is, I haven't upstreamed it yet. TinyGrad is very particular about their line count. I've iterated through this a few times. I'm currently at one new file at about 300 lines of code. And one of their files for the NV backend, I've changed. So I'm at about 16 lines and deleted 8. Pretty close to hopefully submitting for PR, see if they want it upstreamed. I mean, even if they don't, I'm having fun using it. I like using it. But we'll see. Hopefully, cross your fingers. Hopefully it gets upstreamed. And then, actually, I failed to mention this earlier, but going back to compute bound, memory bound, and overhead bound. Again, most of the time in GPUs, you're going to be in the compute bound, memory bound battle, depending on what you're running. Especially, I mean, if you're talking LLMs, forget about it. You're almost always on the compute bound side of things, or at least for the most part. But for that neural network we were talking about, it's a much lighter model. It's only 250,000 parameters. So that is so small, to be fair. Even running it on some of these Orins, I mean, that's so much horsepower for such a small model. I mean, technically, even on ARM devices, if you've ever done, it's a Neon, SVE, it's some of ARM specifics for doing floating point operations. I mean, with the small enough model, you could even do it on an ARM chip as well, if you wanted to. But one of the cool things in principle, though, with these small models, that overhead that you get can be one of your limiting factors. And again, this is I'll mention in this slide, don't read it too deeply. This is like one-man show. This is like a fun side project I've been working on. But I did benchmark my model versus PyTorch and TensorRT. And on this neural network, because it's so small, because of that, we skipped that overhead that they might have to have in their CUDA runtime. I was able to get at least better performance with TinyGrad, which is pretty cool. But to be fair, thank you. But to be fair, it's very niche. I'll even show in this slide. I did a bunch of other models for fun, different sizes. You can see there's kind of like at least from what I've been able to tell. And again, I'm not like a whole lab. This is just me having some fun. From what I've been able to see, when you're able to optimize first principally that overhead bound side of things, you can actually see that for smaller models like convolutional neural networks and some of these smaller ones, you can actually compete with the big dogs. Again, TensorRT, I didn't even mention it, but TensorRT, I mean, that's built by NVIDIA. They're a $4.42 trillion company, tons of engineers, tons of money. Here we are with the library that's 20,000 lines of Python code, very few dependencies. And here we are competing with the big dogs, at least for some of these smaller size, the MLP models. Pretty cool, pretty exciting. And again, part of it is being first principled, right? That's one of the things I love about TinyGrad. You're really trying to really go to the source of like, how does this work? How does this run? And how can we essentially optimize it or make it faster? And then just to reiterate, even though this was kind of an example to keep us grounded, it maybe wouldn't necessarily translate to better performance. You don't know until you test it. But anytime in engineering, when you're able to find optimizations and speed up certain parts, it's definitely a win and definitely things to look at. But anyways, thank you. Yeah, that's my presentation. Any questions from you guys? Go ahead.
Did you build the drill?
Oh, great question. Oh yeah, I should mention too. So the dev kit went on sale around Christmas time, so just like 3 months ago. I bought it. I didn't quite catch the sale in time, but I still got it from a scalper at a decent price on Amazon. So this has actually all been quite recent. It was like a New Year's resolution goal that I had, which was to build more this year. First, principally though, I actually do want to build a drone. This was more on the hardware software side where I've been just kind of exploring things I could do. But there's actually a maker space in it's Orange County. It's by the airport, by the Orange County Airport. And yeah, I actually, fun side project. I do want to go first principle, vertically integrated, and I do want to build my own drone. I think it'd be kind of fun.
So when you did your tests, your benchmarks, it was all simulation?
Yeah. So the benchmark I did, the code for this paper, they open sourced it. And so I actually was able to take their Python code. I switched out, actually I should have mentioned this. They actually use PyTorch in their code. And they weren't even using CUDA graphs as a way to make PyTorch run faster. They were using PyTorch Eager. But for their use case, especially what they needed it for, it was actually fine. But yeah, I took their Python code, switched it to TinyGrad, and then I benchmarked mine versus theirs. So yeah, this was running their model. I ran the neural network, but I also took most of their Python code I just took over, and I ran their
whatever perf test they run, same test.
Yeah. But and the one, and I kind of mentioned. This is in principle because they actually ran theirs on an older version of NVIDIA dev kits. Theirs was a TX. I'm working on, this is the high-end AGX Orin. This one can actually simulate smaller Orin modules, but Orin is like one of the current ones that NVIDIA sells. So they were doing one on one that was sold, I think, from like 2017, 18, 19. So a couple-year-old model. So if anything, too, I didn't want to, that's why mine is more first principle, just trying to take their code, seeing on my device, can I be PyTorch? Can I compete with TensorRT? And then from there, I would definitely have to, I would have to either take their drone or get a hands on one of their modules and benchmark it. Yeah, so this one's just more of a first principle. Hey, are we competing? Are we running that model a little quicker than others could?
So this is my last question. So you had to write the ioctl calls to bypass the CUDA runtime.
Yeah.
And I saw, you're just calling into the NVIDIA kernel module. It's right there. And you want to upstream that to TinyGrad, the work I did to do that as part of the NVIDIA backend. So that means that TinyGrad either doesn't do the ioctl calls, or you don't do the ioctl calls for this Jetson.
Oh yeah, great question. Yeah, this one, let me go. No, that's a really good question. It's kind of all the way back for one of these. Yeah, so TinyGrad, they have essentially all the right ioctl calls that you'd want to call, but theirs were for a different driver. And so actually, maybe think about it this way. TinyGrad did the work. If I go to this slide, TinyGrad did all the hard work for this diagram on the left, where you get the GP FIFO, the push buffer, your QMDs, and your cubins. TinyGrad essentially did all the hard work for that part, but in order to get that memory right, the MMIO, and in order to know how to work with the push buffers and where to put them, that's what the ioctl calls essentially set up for you.
So they were using a different driver.
Yeah. So TinyGrad, theirs works on desktop drivers, and then I took theirs and I was able to essentially map it and get it to work with a dev kit drivers. Yeah.
Great.
Any other questions?
Yeah, I also found that the sorting multiple values, like how these match set, is it provide chosen point by the.
Oh yeah. No, great question. Yeah, in TinyGrad, they're very particular about their code quality and count. I maybe should have included a line when they run their Python code, they pass it in as a command line arg or environment variable. So even the upsource one that I tried to do here, this one right here, you would actually never see this if you would run nv equals 1 and then run your Python command, and it would handle everything under the hood for you. Because they actually have some of their other accelerators. You actually, you literally just pass in NV equals 1, or you can pass in CUDA equals 1, depending on the device. They make it very like, turn on that accelerator and it's gonna work under the hood for you. Yeah. Yeah, and that's why even when I was talking about their ops.nv, that one works for desktop GPUs. So I made essentially a separate class for, I called it Tegra, for Linux for Tegra. And I took this class and that's my, the 16 and 8 change. Yeah. I basically tried to minimally insert it in certain spots so that anyone that's running this, it would work flawlessly, seamlessly if you're on the desktop GPU. And then if you're on a dev kit with the system on chip, it will be able to tell, and it just switches to the file that I had. Yeah. Go ahead. Yeah, question.
Is there, once you actually start doing inference and like have a loop over doing a bunch of inference,
Yeah.
what sort of system call overhead is there, or is it just like set it up and ready to roll?
Great question. That's actually a fun question. Let me go to, yeah. So when you ring the doorbell, the GPU is actually going to go to that ring buffer, and I actually didn't mention it, but this gput, you're also incrementing essentially the almost like, imagine people waiting in line to get food and you get a ticket number and your ticket like 22. So when you tell the GPU, you actually increment that count. So the GPU, when it gets the doorbell ring, it essentially can go to this ring buffer and it knows this is the work I need to do. Like this is the work I need to process. And then, oh, actually remind me what your question was again. Sorry.
Yeah, what other system call overhead is there
Oh.
in the inference process?
Yeah. And so in the inference process, so there's two ways, and it's on this hardware queue side. If you don't do anything, they'll sometimes call it CUDA graphs, or if you're actually, let me start with that. If you make the graph, you can actually essentially see every pointer in that ring buffer. It points to a push buffer, and then those can have different. That's a buffer that has different like sections in it. If you record all those from the beginning, you can actually essentially combine them all into one. And so the GPU would only have one thing in the ring buffer go to that, and it runs them all in like one go.
So rad.
Yeah, so that one would reduce the overhead, but exactly. But if you don't do a CUDA graph, or if you don't do in TinyGrad, they put a decorator, that TinyJit. If you don't do that, then you're gonna individually have more pointers, in your ring buffer that it's gonna have to go through and process. But most of the overhead actually, even without that overhead, you can see I actually did some stuff with a C hot path, we'll call it. Come up to me and talk to me about it after.
Yeah, sure.
But even without that, even without optimizing for that, you still get really good performance. But most of the overhead bound stuff that we're doing is you do the ioctl calls once at the very beginning, and then once you're done, you essentially get that doorbell that you ring, that right, and from there, it's just a game of getting it all set up in the right spot, ring the doorbell, and then from there, it's like a GPU kind of compute bound. Yeah. Any other questions? Hopefully. Okay, well, hopefully you enjoy the talk, enjoy lunch. Feel free to come up to me, talk to me after, and hope you guys have a good day.